Welcome to my video submission for my 489 preliminary report. I've been working on Meap, which is a mechatronic ensemble arrangement and performance system. The system is designed to improve the usability and accessibility of mechatronic instruments, like mech bass over here and drumbot over there. With Meap, the idea is that musicians who don't necessarily have a technical background will be able to configure and interface with these instruments to create musical performances, which previously has not been possible due to the technical barrier these instruments have. So a big requirement for Meap was that it should be entirely usable, both the configuration and performance aspects of the system, within a musician's DAW. A DAW is a digital audio workstation, and it is typically where musicians will create and compose music. DAW softwares that are common include FL Studio, Logic, and Ableton. Ableton is what I use here, and they often have different tracks here from which you can compose sections of music by inserting MIDI notes. And typically these MIDI notes would be sent to a virtual instrument that just creates noise within the DAW, but Meap will change this paradigm a little bit by sending this MIDI information over a network to a server, which will then distribute those MIDI messages to the correct instrument in the correct format. This functionality can be seen in the architecture diagram here, where we have got the user's computer, which has a DAW loaded up, Ableton for example, and there will be a selection of plugins here that they can load into a DAW track, such as one of these here. The configuration plugin will be used to configure new mechatronic instruments and will require the user to enter certain information about their instruments and also run a latency routine. More on that later. It'll also provide a performance plugin, which will be predominantly used when performing with the instruments. A performance plugin will be placed on one of these tracks. It'll ingest the MIDI, it'll send it over to the server, and then once in the server, those adjustments I was mentioning before will be made, the buffering to the MIDI messages and also deciding which string potentially it should be sent to. And then once those have been made, this MIDI will then be forwarded to the firmware of each mechatronic instrument. So under the hood in the Meap server, we will be utilizing the MechSync engine, which was originally developed by Anfree last year. It uses green threading to asynchronously buffer MIDI messages through instrument-specific nodes, and this is how we're going to achieve real-time playback. The first prototype feature I'm going to be running through is the ability to dynamically add and remove nodes to the graph within the Meap server via TCP commands to an API. Unlike the original MechSync, which required configuration files at startup, this will allow musicians to modify the ensemble setup on the fly, which will be a key requirement for this project. Sweet, I'll just run through this configuration now by adding a 2-second delay node to the Meap server. So we'll start the Meap server prototype with this command here. It should kick things off. If we then come over here, we can send it these commands here. This is the add node command, and we first need to create an input node which can receive MIDI information, and we'll just send it to the correct address, and we should get a, there we are, test input successfully added. We'll then add the actual delay node, which we can specify to have a duration of 2 seconds. That's been added successfully, and then we'll create an output node, which is where the MIDI information will flow out of and eventually should be automatically directed to one of these instruments. There we go. Next we need to bind them together so that the graph knows to send MIDI information from the input node to the delay to the output, and so on. So we'll bind the input with the delay, there we go, and we'll next bind the delay with the output. Great. So we've now added a input node, a delay node of 2 seconds, and an output node to the Meap server dynamically via TCP. This leads me on to the next prototype feature that I've been working on, which is the ability to take MIDI information, such as the MIDI information in this blue track here, from a DAW, which is Ableton here, send it over a network to the Meap server for it to then pass it into the input node through the node chain and then pass it out as MIDI information through a MIDI out, which will eventually be sent to one of these instruments. To do this, I've developed a prototype plugin, which is here, MIDI to OSC, and let's give it a go. So to make it work, you have to give it the name of the input node in the Meap server, and then click confirm. Sweet, so now it will take MIDI information from its track here, pass it over the network via open sound control messages actually. This will then be received by the server, it'll pump it through the nodes and then into the output. And then we're just capturing this output here, which is called test output, and using it to play a piano. So if everything works, when I press play, this MIDI information should be delayed by 2 seconds. Let's give it a go. There we go, looks like it worked. Alright, let's give this prototype plugin a go with Meap here. So sending Meap performance MIDI messages over the network from the DAW. As we can see here, we've got some MIDI information in red. We've slapped on the prototype plugin here, and we're going to confirm that Meap is the input device. We'll be using a hard-coded instrument node written by Anfree last year that does the string selection and MIDI buffering. And all goes to plan when I play this. We should send this MIDI information to Meap here. Let's give it a go. Off it goes. I'll just put the microphone up. Very nice. So the third and final prototype that I'd like to showcase today is the latency detection plugin. So a big part of the configuration process of a mechatronic instrument is figuring out what its latency is. How long does it take to actually sound a note after you've sent it a message? We need to figure out what these timings are so that when we want to coordinate the ensemble, we know how much to buffer each instrument's MIDI stream by. So as we can see here, we have got the latency detector prototype. I'm going to demo it with the kick drum of DrumBot, which should be around 2 seconds if all goes well. I'll set up the camera now. So we can see the kick drum of the DrumBot is here. And the way this plugin works is it takes the audio stream in as opposed to the MIDI stream, which is the microphone you're hearing right now. We're going to send it MIDI note 36, which is for kick drum. And what it does is it will send the MIDI note, record 5 seconds of audio coming in, and then it will find the time between the message being sent and the peak in that audio. This process will occur 10 times and it will average the result. Alright, let's give it a go. Just going to set this microphone up here next to the sound source so that we can get an accurate result. And there we go. After 10 trials, it has decided that the kick drum has a latency of, there we go, 2.01 seconds. So that is the latency detector prototype plugin in action, which will be used for configuration.